Thanks everyone, it's good to be here. I should preface this with a little clarification. I am an engineer, I'm not a geologist. I know just enough about geology to be dangerous. And so feel free to jump in with any questions or clarifications you have on something that I might not have made clear enough, and I will do my best to answer it. And if I have to follow up with you to get you a better answer, I am happy to do that as well. But what I'd like to talk with you a little bit about today is the improvement projects that's been going on for the Washington Park reservoirs. Since you guys are here in town, you've probably been a little bit aware of some of the construction that's been going on for the last few years up there. And the reservoir came online this summer and it's flowing water to the city now, so that's great. And I thought this would be an interesting time to give you an update on how that process went about and some of the history of the site, because there really is a ton of very interesting history for this site that I really didn't know about until I started to get involved in the project. I've been involved with the project since 2013 when we started doing the design work for it. And I'm with Cornforth Consultants. We're the geotechnical engineer for the city on this. So today we'll talk a little bit about the Portland water system and the history behind that, as well as the slide itself. And we'll probably spend a little more than half the time just on those two pieces with the history, just because there's a lot to learn there. And then we'll talk about the current improvements project, what we did to accommodate the ancient landslide at the site, and how it performed during construction. And real quick, I'm just gonna check the time. How long do we have here today, John?
You have until about 4:20.
4:20, including questions?
So yeah, that gives us about 10 minutes.
Okay, great.
So
Sounds good. Just want to make sure I don't get too long-winded here. So site history, I'm showing you guys here a map of the city of Portland, more or less, if you want to call it that, back in 1852, when it wasn't too big and developed here. So Portland's just kind of shown as this rectangular general area on the west side of the Willamette River. And we've got this road out here that is now more or less Burnside. And then this Tualatin and Portland and Valley Plank Road, this is now more or less 26 shown here. It was enough of a city to at least have a city park back then. So that's this area called out in here. And that's now part of Washington Park. And that's generally roughly the site of the reservoirs that we're talking about today. I'll show you here, there's some faint lines that these are tributaries here to Tanner Creek. And these were what formed the drainages where the reservoirs were constructed up in the West Hills there. Today, or I should say 5 years ago, this is what that area looked like here. So we're down to the right downtown. Just up at the base of Washington Park, we have reservoirs numbers 4 and 3 here. And then moving uphill, there's the Rose Garden and the Japanese Garden. And if you go all the way over the hill, we get over to the zoo. Those reservoirs now look a little different, obviously, and we'll show you some photos of where they're at. But this site was selected back in the late 1800s as they were planning out the water supply system for the city of Portland. As you know, Portland gets its water from the Bull Run watershed on the northwest slopes of Mount Hood there. We have the natural Bull Run Lake up there, and then a couple of man-made reservoirs, numbers 1 and 2 up there. And then it gets gravity fed from there through a conduit down into Portland. Makes some stops on the way at Kelly Butte and Powell Butte, and then goes under the river and up to Washington Park reservoirs. And they picked that location originally for a few reasons. One is it was a pretty ideal elevation for them. Washington Park, the upper reservoir is at about elevation 293 or so. And that was just about the highest that they could gravity feed water from their Bull Run watershed without having to pump it. When we were doing the design on this, we were looking at whether we could raise the elevation of the reservoir even say 4 or 5 feet just to make some certain construction aspects easier. And the Water Bureau looked at it and said, we're going to have some operational issues with feeding water, even that extra 4 or 5 feet. So they were really right at the limit of where they could get their gravity feed. But it also provides a good pressure for the downtown area. And there were some, I guess you could say, they had some opportunistic valleys up there that they could use to construct some reservoirs. And so they saw it as a good site back in the 1890s, and they took advantage of it. So they started building the conduit for the first feed down from the Bull Run watershed in 1893. And this was conduit number 1. It carried about 25 million gallons a day. And about the same time, they started construction on the reservoirs. So this is a photo of construction of reservoir number 3, or dam 3 is being shown here. These are mass concrete dams, so just their own weight is what holds them steady here. They've got a lot of formwork in place, and they've got this working platform up here where they're mixing concrete and then conveying it down to the pour by chutes. We're looking to the east here, so towards the city of Portland, downhill, and you can see that the abutment at this east end is some pretty decent basalt. We got a little bit of columnar basalt in there that they were able to found this end of the dam on. And then it starts getting a little more weathered and funky looking over towards this side here, but for the most part, they had a pretty good foundation. You look over on the other side, we were just in unconsolidated overburden materials over here. So some fairly stiff silts and some gravelly materials over on this end. They never found rock, but oh well, it was good enough for their purposes, and they went ahead and put the west end of the abutment right there. After they constructed the dam, they laid the slopes back on the valley that was just upstream of there, lined that with concrete, and had a reservoir. So this is a picture of Reservoir 3 as it's nearing finished construction. You can see there's still a little bit of work going on in the gatehouse down here. This is dam 3 here that we were seeing being constructed earlier. And then there's this little feature here, right in the middle of the west slope that was not on the construction drawings. And so it turns out that they had some cracking starting to form of the concrete on the liner in the west slope there as they were getting near the end of construction here. That had been an area that had had some higher groundwater, a little bit looser materials, and they thought, okay, we've got this little local stability issue here. So they went ahead and put this large concrete buttress against the toe of the slope here. And then they dug a tunnel back into the hillside behind there. As best as we can tell, it's a bit of a horseshoe shape kind of locally to this area. And the idea was to get the water out of this localized zone. So they're thinking about the right things, right? For a local stability issue, they're thinking about getting water out of the slide, getting weight on the toe, all the things that we still would start out with as you're looking at slide remediation. And then patch things back up and finished out the reservoirs. So this is a photo of Reservoir 3 and 4 looking from the south end of the site. So this is dam 3 from the opposite side here. And that buttress is against the west slope over here. And then the lower reservoir here, Reservoir 4, is damming off the other tributary of Tanner Creek that kind of ran up this way. Wasn't too long though before they started seeing some more issues come up with the concrete lining their reservoirs here. So this is that buttress again shown. We're looking from across from the other side of the reservoir there. And we've gotten some large cracks that are starting to form and some displacement through the concrete here on either side and up through the parapet wall. And if I squint, I think I can see some distress up here in this little service road they kind of cut into the hillside up here. So they started realizing they were having more sliding ground issues, as they called it. And we're having similar issues down at Reservoir 4 too. So there's a couple of things happening in this photo here. We have more of a superficial slide of some materials right here on the face of the slope where this cut was made. And that kind of pooped out down here and spread some material down. And that's a more dramatic piece of the photo, but it's not really the main issue. If you look down here where the concrete is really starting to crack, you know, that was the sign, the indication that something much more significant was happening. So they started looking around uphill up here thinking, okay, if we have a slide issue, there's got to be some ground cracking. We need to be able to see a headscarp somewhere or something like that. So they were poking around all up this road up here and the next road up the hill from there and just weren't finding anything. And started trying to maybe thinking, okay, we might be able to talk ourselves out of this being a landslide. Until a month or two later, someone was further up the hill where they had a cable car line that was being constructed. And they saw that the tracks were significantly out of alignment. and they realized they had a much bigger issue on their hands. So when they found that, that kicked off a series of investigations and remediation measures in order to try to stabilize the slide. And fortunately for us, they documented everything they did in quite a bit of detail in a paper that was published in the 1904 ASCE journal. They called it a phenomenal landslide. This was written by D.D. Clark, who was the engineer for the Portland Water Bureau at the time. And it was about 100 pages of just all sorts of details, from things that they found while they were doing it, all the way down to what he paid the workers who were digging holes in the ground for him. It was really a tremendous amount of information for us. So I'm going to show you some figures today from that paper, just because they really did a good job of helping to characterize that slide, even with the methods they had available at the time. So this is a site plan from that paper. Reservoir 3 and 4 are down here. Uphill is to the left in this photo. The first thing they did is they realized they had a bigger issue, is they established some ground survey. And then they started drilling a bunch of 6-inch vertical holes in the ground using sort of a churn drill type of apparatus. And they did their best to characterize the materials that they were getting back based on that drilling. But the other piece that they did that was probably more valuable to them was after they completed each hole, they would pound in a 6-inch diameter steel casing into the ground down to about top of bedrock. And then about once a month, they'd come back and they had this like plunger type apparatus they would run down the inside of the pipe and try to figure out where it was pinching off. So it was a very crude earth deformation casing or slope inclinometer. But using that, they were able to determine what ground was moving and at approximately what depth. So they identified that the landslide was about 1,700 feet long, if you measure horizontally, about 1,100 feet wide at the base, and extended about 350 feet or so vertical elevation uphill. It didn't feel like they had characterized the slide well enough to understand what it was moving on or what was causing it to move at that point. So with the methods they had available, the next option they turned to was digging a bunch of shafts through the slide. So each of these yellow diamonds represents a shaft about 3 foot square that was hand excavated down to the top of bedrock. And so that was anywhere from about 60 to 120 feet down. They hand excavated each of these shafts. And what they found was in almost every shaft, right on top of bedrock, they had a clay deposit that was just exhibiting some signs of considerable movements. We had a lot of slickensides and striations on this material here. And they didn't really have a way to characterize strength, do any strength testing back then, but they really did make an effort to try to understand what this material was and how it was behaving. They usually referred to it as a blue clay or a red clay or something like that. So maybe not in the parlance we would use today. But you can see they had some very good photos of it in this lower right-hand corner. They try to reconstruct the angle that it was moving on down at the base of the shaft there, and figure out where the slide plane was going. And so from that, they drew, from all these shafts here, they drew some cross sections showing where the top of bedrock was and where things were sliding. The other thing that they found in one of these excavations is just a little tidbit, is they found a tooth that they sent off to the National Museum in Washington, D.C. and was later classified as a prehistoric camel's molar. So there were once camels in Oregon. But overall, they advanced, a couple dozen of these shafts. They were able to figure out generally the materials that were down there and what it was sliding on and the mass of the slide. They estimated in total they had about 3.5 million cubic yards of material that were moving downhill in this slide. And just as a bit of reference, the amount of excavation that they did at the toe that triggered or accelerated this movement of the ancient slide was about 60,000 cubic yards. So a fairly small change in the toe condition caused a very big change in the stability conditions. And when you're starting out with a factor of safety of 1, it doesn't take a lot to tip the scale. So this is a section of the lower part of this slope, just above Reservoir 4. And as they're starting to think about what they believe is causing this slide and what can be done about it, this figure was somewhat informative to me as to their thinking. So down here at the bottom, they've got a material they're calling just a yellow clay. Overlying it, they have this blue clay called out, and then a little bit of a sand layer. But then they also have this area in here that they describe as quicksand. So anytime you have a landslide and you've got something at the toe you're calling quicksand, indicating some sort of very loose saturated condition, I think that tells you something about the role of water in that slide there. They also had put some riprap against this lower part of the cut slope here, apparently in order to stabilize it. And so this is an old photo. You can see that rock inlay that's basically been put in here with a series of herringbone drains that are trying to get that water out of the slide. And so as they started thinking through what they might do to stabilize the slide, one of the first things they tried was another small tunnel. So this tunnel was just dug in from the slope of the reservoir here and didn't extend too far uphill, a little bit further laterally. And it was back through the sand layer here just below that quicksand they called. And this was their first attempt to drain some water out of the slide to see what would happen. They had one other data point that gave them some clues to the role of water in here. And that was for each of those shafts I was showing you earlier, they encountered groundwater fairly shallow, especially up here in the upper half of the slide. This water table was often fairly close to the ground surface. And they were doing hand excavation methods, right? So they don't have any way to work underwater. So they had to pump all these water out of their shafts in order to keep working. And some of these shafts, they just pumped a tremendous amount of water. I think it was maybe this number 4 shaft up here at the top of the hill that they pumped for 9 months straight before they could get it dry enough that they could continue to finish the excavation on that. So just millions of gallons of water were getting pumped out of the ground here. And they noticed with their ground survey that while they were pumping, that the slide rate of movement was decreasing. And then when they stopped pumping at the end after they finished the shaft, the ground movement started to kick back up again. So they decided to expand on their earlier tunnel idea and to start out constructing tunnels from the bottom of the hill up to the top, more or less following this shear zone, and then gravity draining water out of the slide. So starting around 1900, they constructed sort of this main stem tunnel up here from Reservoir 4 that ran up near the center of the slide and then had a few branches at the top in order to start getting some water out of the slide. And then a few years later, they came in and added some more ancillary tunnels to do some more drainage, especially along the lower half there. So I think they put about a half a mile of tunnel in that first round in 1900 to 1901, and then added another 4,000 feet of tunnel a few years later. And they were measuring discharge from these tunnels, and we're getting anywhere from 18,000 to a little over 100,000 gallons a day of water coming out of these tunnels. And it really did a fairly good job of eventually draining a lot of the water out of the slide. And they kept very good records again on things. And so they kept records of what was the rainfall each quarter and what was the slide movement during that quarter. And if I take this old image and translate that to something that's a little bit easier for us to understand, we can see that, initially they started these investigations when the slide was just booking its way downhill about 15 inches a year. And the early months was even higher than that. They start dewatering for some of these shafts, and we have that rate drop by about 90%. They stop dewatering and that rate starts to kick back up. So they put these tunnels in, and it brings it all the way down to about 1/4 of an inch a year. After some wetter years, that started to kick back up, so they constructed those additional tunnels. And then since then, that rate has been fairly low and slowly dropping until it's about 1/8 of an inch a year or so. Right now, it just continues to creep down the hill a little bit every year. Those smaller movements still add up over time, and so the reservoirs have continued to experience some distress from that movement. And that brings us to the current improvements project, where in addition to addressing these ongoing landslide impacts to it, we have aging infrastructure. That system is still 130 years old, no matter how you shake it out. And we also have an emphasis right now on improving the seismic resiliency of some of our key infrastructure. This water serves 3 hospitals, a number of schools, and is the key firefighting water for the downtown corridor following an earthquake. And so the city wanted to make sure that it was able to withstand a large Cascadia subduction zone event. And we also did have some federal drinking water quality regulations that needed to be conformed to. And so all of these factors came together to make this project happen. So this was the concept that was put forward at the beginning of the project. We have a site that's on the national list of historic places, and so we can't change the historic character of the site. And so this upper reservoir, Reservoir 3, was being converted to an underground buried tank, but then we'll put a reflecting pool on top of it so that it still appears to be an open reservoir. And then the lower reservoir, the city didn't need as much storage as it had originally constructed at this location. And so this one has been decommissioned. It's being converted to a stormwater, a lowland habitat area. And then we'll have a small reflecting pool as well against the dam there. So I'd mentioned that we're working to keep that historic character. So this is a picture that was taken of Reservoir 3 from the north side prior to this project occurring. And this is what we're going for at the end of the project. There's a lot of pieces that have to come together underground to make this happen. And I think underground is where a lot of the interesting stuff happens. So we have a buried tank, essentially, that is going in here. And on the west side, we have a system to mitigate for the landslide. We'll talk about that a little bit more. But in order to get this reservoir away from the toe of the slide a bit, we had to push it to the east. And so that required some excavation here. And we have a couple of temporary shoring systems in here. So a temporary tieback wall that went in here, and a permanent tieback wall that went in down here. I'll show you some photos of that. And then this reservoir is supported on a network of about 176 drilled shafts that go down to bedrock. So our design approach for this was kind of unique. And it was unique because we had the luxury of having all this history about the slide. We have information on the slide that goes back over 100 years. And we have more or less modern readings of movement of the slide that goes back all the way to 1987, when we installed some slope inclinometers that have been measuring the ground movement since then. And you can see that that movement has been very consistent over the decades. And that's largely because of the drainage that was provided originally. It really mitigates the amount of groundwater fluctuation that we see and keeps the slide in a fairly consistent state there. And so we'll have, this move a little bit more in the winter than it does in the summer, and it will move a little bit more in a wetter year than it does in the drier year. But overall, it just kind of keeps creeping along, right about 1/8 of an inch a year or so, all the way up to the time of construction. So because that drainage has been so effective, one of the keys to our design is not to do any harm to that drainage, make sure that it keeps functioning. And if we do that, then we can choose to accommodate the movement of the slide rather than trying to fully arrest the slide movement. So the system that we came up with for this is starting by shifting the reservoir a little bit to the east, away from the toe of the slide. Against the landslide itself, we constructed a mechanically stabilized earth fill here. And then we left a little slot between the reservoir and the MSE fill here and filled that with geofoam, which is just an engineered styrofoam. And so instead of this landslide imparting a very large and unpredictable force on the side of the reservoir as it moves, instead it's pushing on this foam, which will crush and impart a much smaller and more predictable load to the side of the reservoir. So this is a picture of what that looked like going in. I mean, it's not a, I wouldn't say it's a sophisticated technology, but it's an approach that hadn't been done before. And so it was something that we were learning as we went on. And so we see the tank on the left here, that's the reservoir. Then on the right is this MSE fill. And in the middle here, we're just filling that in with some these large engineered foam blocks. You can see them exposed over here as well. So these were designed for a design life of 75 years, including a Cascadia subduction zone event. If we don't have an earthquake in the next 75 years, it'll last a lot longer than that. And at the end of the design life, if the Bureau would like to keep the water functioning or the reservoir functioning here, it can be dug out and replaced, and they can continue keeping that in service. We did put in a couple, 3 different stations where we're monitoring the actual movement and the compression of this foam layer so that we can keep up with what the design life remaining is. So I'll take the time we've got left and take you a little bit through construction here. You know, it's one thing to put something like that on paper, and it's another to get it into place without poking the bear too much. You know, we saw what happened the first time around when they just went in and started making some large cuts and fills in the area. We wanted to try to avoid the mistakes of the past there. So we're going to take a look at how the landslide responded to our construction. We're going to look at one instrument that was in the landslide in particular. We call it SI8. And this is an inclinometer that is drilled into the ground and grouted into the ground. If you haven't looked at an inclinometer before, it's just basically a 3-inch or so diameter round pipe that has some grooves inside that we can run an instrument up and down and use to profile the ground. And so as the ground moves, it deforms this casing, and we can pick up those deformations, and it might give you some readings, something like this, that show you how that ground is deforming over time. So these were readings from SI8 prior to construction. During construction, we placed an in-place inclinometer, which is an automated piece of equipment down the hole at the shear zone there. And so we got some near continuous data coming back that tells us exactly how the slide is responding to the disturbances that we're making at the toe. And overall, the approach to getting this landslide mitigation system in place, the first thing that had to do is we had to drain that reservoir there. And that might not seem like a big deal, but that water is actually pushing against the toe there. It's providing a little bit of stability. And taking that water off the toe ends up creating a little less than a 1% difference in factor of safety for us. And so that's significant enough that we want to make sure that we compensate for that in the long term. When they have to strip the liner, we dig a little slot at the toe. We put in a little bit of concrete, and this is what we're calling a toe block. It just gets us kind of up and out of the excavation so we don't have to dig so much into the hillside in order to get our base width that we need to have a stable fill. Then we do have to take a little bit of material and excavate out of the landslide toe. And so when we do that, we use closely sequenced construction methods where we're recognizing that this is a destabilizing activity, and we're taking stabilizing activities and sequencing them as close as possible to that destabilizing activity. And at the same time, we're limiting the length over which that can occur. So we start building back that MSE fill as fast as we can, and we build it up until we're compensating for the effect of that cut. After this wall is built, we can go ahead and construct the drilled shafts for the tank in front of the wall. Go ahead and put a drain in, put the reservoir, and then fill it in with foam. So here's some photos of what that actually looked like and what the landslide response was to that. So this reservoir here has been drained. Nothing else has happened to the slide yet at this point. And so the landslide movement is just moving along at more or less its current rate, maybe slightly accelerated because we've taken a little bit of water off the toe, but more or less its baseline right there. And the first thing that we do then is strip out that concrete liner over about 50 feet of the reservoir there and dig a little slot at the toe to get that toe block started. So this is a very small excavation. We took out maybe 50 cubic yards of material, about 5 dump trucks worth of dirt from the bottom. And we took off some concrete liner. But even so, we saw a response from the landslide. So we made that cut and we saw immediately a little lurch occur in the slide. And then we poured back concrete that same day, got some weight back on the toe, and we saw the slide start to settle down again. Then we repeated that process in 50-foot segments, moving from south to north. And with each one of those, we saw a similar type of little jump in the landslide behavior that settled down as soon as we got some weight back on it. So this landslide is responding in a very logical and predictable way to the impacts that we have at the toe. I don't want to say predictable in the sense that we can exactly predict the magnitude, but it's behaving consistent with our interpretation of how the slide should respond based on our characterization of the slide. The next step then is to cut into the hillside a little bit in order to get the base width for that MSE fill. So this is a little bit more material. Now we have a few hundred cubic yards of material coming out. And we didn't take all that dirt away. A lot of it we just flopped over to the hillside next to it and tried to keep that weight on the toe of the slide, just in a little bit different location. But it is a bigger impact, and so we saw a correspondingly larger impact to the slide movement there. So as soon as we started in on this, then it was go time, where you start building that MSE fill in, and they had to build it to a certain level before they could start making the excavation for the next segment. But our objective at this point is to start getting that weight on the toe of the slide as quickly as we can, so we can catch up with that slide movement there. So I'm going to zoom out that figure on the right a little bit so we can see where we're at. That green arrow shows that point in time. And we just continued with that approach where they're building up that fill and continuing to excavate to the north there. So at some point, we finally started to catch up with the amount of weight we had taken off the toe and compensate for that. And then that lower block of the slide began to settle out. So this was an interim condition for that fill for a while they constructed the drilled shafts down in the bottom of the reservoir. And then eventually they built up that wall to full height at the north end there. I do want to keep those movements in perspective. You know, I was zoomed in a lot so we could understand the behavior of the slide. We're looking at it at a very close scale. But before we had started into this at all, we had stepped back and taken an assessment of the situation with the owner and said, okay, what levels of movement are actually going to concern us here? And we had established these different thresholds of evaluation where we step up the monitoring and response to some accelerated movements, some preparation where the contractor had to begin to prepare some predetermined steps in order to be ready to act in case something needed to be done, and then an action level where we said, okay, the movements are too high. We need to get some more weight against the toe, get some more drainage measures in, and we need to act to stabilize the slide here. Unfortunately, those little blips we talked about are circled down here. We were able to keep those movements to very manageable levels through the course of construction on this. So just a few photos here of construction, just to show you the other pieces that went into this. I had mentioned the soldier pile and tieback walls that were on the east side of the reservoir. We have a vertical drill here using a continuous flight auger to drill some holes into the ground and set these soldier piles. These soldier piles are just steel beams that get set at regular intervals so that you can excavate in front of them and install some wood lagging, and then these support the excavation. And for taller walls, we'll often install these tiebacks where we drill something that's a little bit sub-horizontal to the ground. We install these steel tendons and grout them into the ground, and then we tension them, you know, maybe 100,000 pounds or something of tension on these ones in order to stabilize those piles and keep them straight and vertical as you're moving down with the excavation. So that wall has been completed in the background of this photo, and they've moved down and are starting to install a permanent soldier pile wall here that would carry the long-term earth loads adjacent to the reservoir. So here they're just repeating that process of excavating, installing this temporary wood lagging, and installing these tiebacks. You can see the first row has been installed and stressed here. And then this was a permanent wall, so it got a concrete facing to carry the long-term loads there. And then they're starting to prepare to install the drilled shafts in the bottom here. While this wall was going in, on the other side of the reservoir was when the MSE wall was getting built, and we saw some photos of that getting brought up here. There were a couple over, I think over 150,000 yards of material that had to come in and construct that. And then they began constructing drilled shafts down in the bottom of the reservoir here to carry to support the reservoir. So these were holes that were anywhere from 3.5 to 5 foot diameter that I got excavated down and socketed into the salt bedrock here. They lower in a steel rebar cage and backfill it with concrete, and then that forms the foundation system for the reservoir. And we had some areas near the center of the old stream channel where the depth of bedrock was fairly significant, up to 70 feet or so. And so we had some very long rebar cages that had to be placed for those shafts there. After they constructed the foundations, then they started constructing the base slab for the tank. They're doing a pour here. And you can see that they're also doing this in segments, working from south to north. And that was another constraint that we put on the contractor as part of the design, because, you know, if you think about how the slide existed, you know, before we were here and impacting it, right? You probably had this creek cutting into the toe. At some point, that slide moves a little bit. It pushes the creek towards the other side of the valley. That stream works its way back in, cuts in at the toe, and it repeats that process a few times. And so we anticipated that there could be potential for some other lower toes than was the one that it currently is moving along. And we didn't want to risk reactivating a lower toe of the slide by digging out too much material at once in front of this MSE wall. And so we restricted them to just constructing in segments again from south to north and completing a segment before they moved further to the north in order to minimize the potential for some movements that we didn't want to see there. The next step was to form and pour the walls of the tank. This tank was up to about 50 feet high at the south end there. And then forming and pouring the roof. That was an interesting challenge for the contractor, because everything you form has to be able to be disassembled and come out this little hole here when you're done with it, because you're boxing yourself in. And this was the finished reservoir earlier this spring. And you can see there was a little slot that was left here along it, and that was the space where we constructed that compressible inclusion, as well as a couple of other small fills that went in at the ends here when they were all done. And so this reservoir was brought online in June, and it's been flowing water since that time, and they finished out those fills since then as well. There was some things happening down at the lower reservoir as well, not quite as much, but a lot of the materials we excavated at the upper reservoir were brought down to where this decommissioned reservoir was and used to fill it in. And like I said, that's being converted to stormwater management area and a swale down there. And then another thing that we were able to take advantage of at the site, because the reservoir was being decommissioned, so we were able to place some more fill down there in the form of some reinforced soil slopes. And what we were attempting to do with this was to get back towards the original ground surface that existed before the reservoir construction in the 1800s. So we knew it was at least in a marginally stable condition at that time. And so since we had the real estate, if we can get back towards that condition, we're going to be substantially improving the stability of at least this portion of the slide. And so we ended up placing about 160,000 cubic yards of material down here at the toe of this part of the slide in order to bring up the stability of this component of the slide here. So that's what it looked like in the finished condition just after it was seeded. So the project has just started in on a 2-year settlement period. There's a number of these large fills that we constructed around the site that are going to be causing settlement and inducing settlement of the materials there. And we have these very sensitive reflecting pools that are going on top of it. So we have to wait a couple years for that all to settle out. And then they'll come back, they'll construct these reflecting pools, some retaining walls and some other visual feature elements. And then they're going to be completing this project in 2025. So that was what I had prepared for you guys today. I'm happy if I save some time to answer any questions you have.